Oh, thank you very much. So, first of all, thanks for letting me speak here, and thanks for coming. I'm pretty amazed that so many people turned up, because I was expecting that, for example, 5 people turn up and will join Alexis Shipilov at his talk. But nevertheless, welcome. So my name is Maciek Próchniak, and I work for Talk. We're kind of not so small, like 90 people software house based in Warsaw. And we're doing many kind of more or less interesting things. In my life at Talk, which lasts for like 9 years, I've been dabbling mostly with integration, OSGI, Scala, and so on. And this talk will be a little bit about integration, about a project which is mostly in Scala, but today we'll be talking about something a bit different. Today we'll be talking about stream processing. So, first, let's look at our domain. Most of Talk clients are in the domain of telco. Like, we work for many bigger and smaller mobile operators in Poland. So let's look. What data do they have? I'm sure most of you have mobile phones, so you more or less know what they are. So the most important one, or at least one of the most important ones, are billing events, right? Each time you make a call, your account is billed, especially when you have prepaid account, but also for postpaid ones. Also, if you make a call, if you miss a call, if you send a text message, all this data is gathered in mobile operators' platforms. Also, with some additional information about, for example, network usage. If you use mobile data, on which pages do you browse? Although this is kind of really sensitive data, of course. And also about localization, with what base transmitter station your mobile phone is connected, and so on and so forth. And also some smaller changes, like, for example, you activate data package and so on, or you change tariff. So how much of the data do we have? Like, billing events for typical large Polish operators, like 3,000 to 5,000 per sec. So not so large amount. The exact information connected with network usage localization, this varies between various data sources, because sometimes static data from mobile phones is collected, and sometimes only when you make a call. So it can vary from this 3,000 to up to, I don't know, many hundreds of thousands per sec. But this is not usually really processed. And account changes are small stream of updates, so we don't care too much about them. So what do we want to do with them? I'll be talking mostly about two large areas. One is real-time marketing, okay? So we want to detect interesting event. For example, you are approaching airport, we expect that you will fly away, for example, outside European Union, and we want to propose you, hey, buy this data package, which will save you some roaming cost. Of course, we want you to be a right customer. If you already have data package, we don't want to send you SMS, so we have to check what tariff do you have, what kind of billing do you actually use. And the most important thing, we want to do it immediately, because in half an hour you'll be out of airport. And for example, if you want to invite you to our next point of sales to see the brand new iPhone, then we also want you to receive the message immediately, right? So it's a idea of finding interesting event and sending message as fast as possible. Of course, there are some additional quirks like GDPR. I didn't hear GDPR mentioned at this conference yet, so remember, it's important. Some messages are regulated by law, for example, when we will bill you more because you did something or you flew away from European Union. The law requires us to send you the message. And of course, the message should be somehow customized based on your tariff or your, I don't know, age or anything like that, right? And another area that we've been working with is fraud detection. There are many kind of, for me, amazing ways how people make fraudulent calls. Some of them are pretty easy. For example, you buy fake postpaid account and you make, I don't know, thousands of calls to Solomon Islands, each billed like 2 or 3 euros per second. Some people send marketing SMSs like thousands per day based on some cheap prepaid tariffs, which is not allowed by regulations. Also, there are many many different cases of SIM cloning that you can use the same SIM number in different locations, or more elaborate stuff like SIM-box termination fraud, where the fraudsters take into account some strange interconnection rules, how much one call can cost in this area and in that area. So these are all the different cases of frauds. And we want to fight them by computing aggregates, right? How many messages this number sent in last 4 hours or 8 hours. We want to know where was his last call happened. Because, for example, if at 10 o'clock he was making a call from Austria, and at 10:05 he was making a call from France, something is probably wrong here. So we want to detect some suspicious transfer, and we want to report to some revenue assurance guys, or in real kind of obvious cases, maybe we can even block the account, right? The funny thing about mobile operators is that they already process all those data by their billing system. This is the core of their business, right? For example, if you have prepaid account, all those billing data has to be calculated almost in the real time to terminate the call if your credit is 0, right? So it's already processed, it's fast, and it's reliable. But the thing is that billing is usually a big black box, right? And it's really hard to make changes. This is such critical systems that any change can take like months and costs like, I don't know, thousands. Okay, on the other hand, all those data is stored in various kinds of warehouses, Greenplum, SAS, Oracle, you name it. And it's quite easily accessible by analysts and so on. They can do reports, they can detect the frauds. But the problem is that the data appears in the warehouse only after, I don't know, a few hours, sometimes even after a day. And what's more, the SLA for this warehouse is probably not so high, so it's not suitable, for example, to make some execution like, I don't know, blocking accounts, sending text messages, and so on. So the challenge that was put in front of our system was it should be process the data as fast and accurately as the billing system, but it should be as easy to use and customize and to, for example, design new marketing plans as in the warehouse, as writing SQL queries. Okay, so this project lasts for like almost 2 years, and we came up with such an architecture. Okay, this is kind of, I would believe, standard architecture for data processing. We have some sources, either from TCP streams, either from files, databases, and so on. We push them to Kafka, we process them with this strange guy, Apache Flink, and then we send it to either to some computation results to warehouses, either to SMS gateways, and so on. Okay, so this is nothing too novel except maybe this strange thing here. Okay, as for the logos appearing at the previous picture, so I'm sure most of you know Apache Kafka, right? And this is great piece of software. If you don't use it for event streaming, then do. It's just, I would say, it never let us down. I would really recommend it. And what about Apache Flink? How many of you know it? Oh, quite a few. And do the remainers know Apache Spark? More or less, right. So Flink is Spark, but better. Okay, I've said it. Of course, better in certain circumstances, especially when it comes to streaming, because Spark is like rather batch, and streaming is just afterthought, and streaming is like first-class citizens, and batch is treated like, I would say, finite stream. Okay, so we've picked Flink because it provides us with very low latency and high throughput. It can guarantee exactly one semantics when we process our events. It can handle really massive states like gigabytes or terabytes of state that can be stored either in memory or on disk. And it has really nice rich API. So this is the problem that all those streaming processors try to resolve, right? When you are in firehose mode, then you cannot use transactions. This is for MS SQL Server. So they have to deal with state and updates of state in various ways. And Flink is one of the most advanced pieces of software that deals with. So when the events are coming, and the aggregates are computed, and then some failure happens, the server is restarted or whatever, then the state is stored somewhere in safe persistent place. So after the restart, it can be restored, and all these windows and computations have good results, right? Also, there are quite a few problems that you have to deal with when you do it manually, like out-of-order events, and also modern stream processors like Flink and Spark can handle them for you using some custom concepts. I won't go into the details because they are not that important for this talk. And this is more or less how you interact with Flink, right? It has nice Scala DSL, right, when you can define how the data flows from the source, like for example, from text file, and then you operate on it like on just like Scala stream, right? You can declare windows, you can declare filtering, and so on and so forth. So this is how developer writes Flink process. And what happens then? Well, the code is put into the jar file, and the jar file is deployed into something called job manager. That is more or less like coordinator of Flink cluster, and then it's deployed to workers. Flink is distributed system, and it runs there. And the job manager can assign certain resources for the process. We can say, should it get like 4 cores or more? So job manager picks appropriate workers. They communicate with each other, and from time to time they send the state to the job manager, which stores it into some persistent location, so in case of failure, it can be restored. So all this is done by Flink, and you really don't have to worry about it, which is pretty nice thing. But as soon as you want to deploy many campaigns, you may start to wonder, how many processes do we want to have? Should we have one global job per all mobile operator, one per area, like one for fraud, one for real-time marketing, one per source of data, because we have many of them, or just one per marketing campaign? It turns out that Flink can do both of the approaches. One is kind of more like microservice approach. We have many processes, for example, each for a fraud case or one process per marketing campaign. And when we want to deploy a new version, we just deploy this new process. And all the other processes are unaffected in Flink cluster. The other approach is a bit more elaborate, but it can save you quite a lot of resources. In this way, you have one larger Flink job, which is kind of highly configurable, and inside you have kind of more smaller jobs. And you have additional kind of controlling stream of data, where when you want to deploy a new version of certain, for example, campaign, the job itself is not restarted, the state doesn't have to be restored, and you just deploy kind of new functionalities. So this is harder to achieve. This is a bit more difficult to monitor, so we stick with the former approach. That is, we have one Flink job per one marketing campaign. And unfortunately, it leads to some resource leakage. This is our production server. So as you can see, like 1,000 threads is probably too much. But fortunately, most of them are more or less idle, so we don't have that much problem with context switching and so on. But there are some downsides to the approach that we've taken. Okay, so this is kind of one of the first challenges of our architectural decisions that we had to make during our project. Most of them were pretty straightforward, but I want to share at least some of them with you. So let's have a closer look at our architecture, right? And let's look at the data ingestion. As I said, we have many sources of data. Some of them are for files. Sometimes we just connect to raw TCP sockets. Sometimes we do something even more elaborate. And then we want to put them into Flink. So if you are kind of beginning Flink user, you may say Flink has many connectors to different sources. It can read from Kafka, it can read files, and you can write your own or connect to JMS or whatever. And this is the first thing to try, but quite soon we realized that we need some additional processing step. Because Flink can obtain data from many sources, but in fact, its primary data source that it works really nicely with is Apache Kafka. So the first thing is to split the processing between data ingestion and then between data processing, and put some Kafka topics in them. And the next thing that we ended up with is replacing this data ingestion process in Flink with, in one deployment it would be Kafka Connect, in another deployment it would be Apache NiFi, and in other some different tools for data ingestion. You may ask, why do we do it when Flink can handle all of that? And the reason is to have kind of separation of concerns. Because Flink has all these connectors, but some of them are kind of, I would say, not so high quality. And if you use the tool that is meant to do the job, like NiFi or Connect, you can get away with it kind of more reliably. And also it leads to better observability, because all those tools have better monitoring tools for monitoring ingestion, for example, from files, TCP, and so on and so forth. Okay? Which leads us to another problem, because here we ingest the data from in a kind of raw form. We put it through Kafka, through some parsing process, and of course we have to kind of do some additional processing, like clearing the data and so on. And the strange thing is that there's another line of work, because all those data comes to warehouse, right? And when it comes to the warehouse, it's also processed in the same way. Probably it goes through some Python scripts, SQL files, ETLs, and it's processed in some way. The data is cleared in the same way, and the code is duplicated. So this is currently our kind of problem, because all the ETL pipelines are in place for like 10 or 15 years. And there's certain anxiety when it comes to replacing them with our new code that runs faster, but it's not so, I don't know, it doesn't believe to be as stable as tested. So hopefully this pipeline would be merged to one going through Kafka, both to Flink and to the warehouse, but currently we have to deal with two different ways of processing data. And then let's look at the execution part, that is sending SMSs, blocking accounts, or accessing some different data stores. So again, at the beginning, we are sending all this stuff directly from Flink processes, and it works pretty well. You can, I would say, invoke any Java Scala code from Flink, and it works. But after a while, again, we introduced some additional layer. So we put all our commands, for example, send SMS or block account, again, to Kafka, and only then we put it into HDFS or somewhere else by Kafka Connect, write some microservices in Akka, or write another Flink process. And again, this is something that is kind of maybe almost obvious, maybe obvious, but still we tried it only after some time. So the benefit that you gain is that you decouple the processing. So for example, if you have 10 marketing campaigns sending SMSs and you want to change SMS sending logic, you can do it in one place. And also failure handling is much easier, right? Because Kafka, as pull-based system that can reply events, is well suited to such things. And when we tried to send to some not really reliable sources the data from Flink processes, that led to kind of difficult problems concerned with back pressure and so on. So now we figured out it's better to first send it to Kafka and then let our service do the job. Right, and then again, observability is better then. Okay, now let's look at the bottom part, that is the data enrichment. Because all these events contain data, for example, about your call. They can contain your phone number or some client ID, but then we want to know what is your tariff, where do you live, and also probably something about your historical data. Do you pay your invoices in time? What was your last invoice or average invoice in like 6 months, and so on. And also there are, of course, many additional dictionaries. If we have your tariff ID, is it prepaid, postpaid, or whatever? Okay, so it seems quite easy. All of this can be put into the database because there are not so many customers, like 15, 20 million. Who cares, right? Let's put it into Oracle. And from the process, of course, we can invoke REST APIs, we can query database, and so on, and be happy with it. Unfortunately, the problem is we have to do it pretty fast. Imagine like having 20,000 requests per second, right? And for example, we have 10 Kafka partitions that more or less translates to 10 threads processing the data. So that gives like 2,000 events per thread, right? Which gives like 500 microseconds per event, which gives like half a millisecond per event. Now, to go to database or to ask, for example, even Redis, which is pretty fast, it can be hard to sustain. So you can think about different ways of handling the stuff. For example, if there's some data that you need for each processing, for example, some ID translations, this is a common case for us, you can do it only once during data ingestion and then enrich the events that you put through Kafka to your Flink processors. This is this works quite nicely when it comes to latency and to throughput, but the problem is that your event can get quite large, right? Because customer profiles can take like, I don't know, 50 attributes or more. So you probably don't want to put all of them through Kafka because you run out of disk. And another idea is to have the events in their original form, but have additional stream of updates of, for example, accounts, right? So we have smaller stream of updates of accounts, changes of tariffs, or package activations, and then cache them somehow in each of the processes. And this is also quite nice approach, but of course this is caching. It has some drawbacks, and unfortunately this is not so well supported currently in Flink. I don't know really how it is in Spark because stuff changes pretty fast now. But enrichment is kind of larger problems when it comes to performance, right? Because having some REST calls or Redis calls that last kind of less than half a millisecond is hard to sustain. Async enrichment is also surprisingly difficult. Up until kind of a few months ago, Flink only supported synchronous calls, which of course also destroyed performance. But even with async enrichment, it's not so easy to get it right. And caching, well, caching is caching. It's expensive and also difficult to get it right. And again, Flink doesn't have full support for such connected streams of updates, right? There's some work in place, but it will take a few months because before it's done, right? So that was about enrichment. Now, let's look about Flink itself, right? As I said, Flink is a great piece of software. It works more or less seamlessly, but you have to know how to use it. And the biggest problem with all of stream processing stuff is, of course, handling state. As long as you don't have any state, you have stateless processes, you're done. It's easy. But once you have to keep, for example, last location, this starts to get pretty tricky because not always the data can fit into the memory. Our machines have like, I don't know, 100 to 200 gigabytes of RAM, but it's not always so easy to, for example, allocate heap, and going off heap is even more difficult. And even more difficult is handling kind of state that is variable in length, right? For example, when we want to be able to measure total duration of calls in like the last few hours or total unique numbers. Now, computing unique numbers or all numbers that were called is even more difficult because the state may vary with which each number, each key. And then we want to process it kind of instantly to generate alerts. So all those stream processing engines has a notion of windows. One window is kind of it's called tumbling window. For example, it's best used to compute how many, for example, calls were made between 1 o'clock and 2 o'clock, 2 o'clock and 3 o'clock. But this is not so nice for us when it comes, for example, to fraud detection. We'd rather use something called sliding windows, which want to help us to answer a question, how many calls did he make in the last, 3-4 hours, right? This is the question that we really want to answer. And the problem is that if you look at this picture, with the sliding windows, each event is a part of more windows than one, because the slides are usually quite short, not like this in this tumbling window case. And even more difficult problem when the case comes to fraud detection is that interesting fraud usually give us skewed state, right? When you have normal client with normal phone usage, he can make 10, 20 calls per day. How many numbers? I would say less than 20, right? So this is small predictable state. But when you have a real fraudster, he can have as many as 50,000 calls per day to, more than 10,000 unique numbers. And this is kind of more troublesome to compute, because how much space in memory do you need to compute all those unique numbers? Quite large. And then the performance starts to degrade, of course. Okay? So there are some approaches to handle this stuff. For example, you can enlarge the slide of the windows, so you compute the aggregates with some certain granularity, which lose some accuracy, but for frauds it's okay. You can ignore events after a certain threshold. For example, if you call more than 5,000 times a day, then you're a fraudster. We don't care how many exactly. But again, this is kind of big loss of accuracy. And also, another approach, a bit more elaborate but very interesting, is the use of probabilistic data structures. This is something we're playing around a bit lately. And it means that there are certain algorithms, data structures like Bloom filters, hyperlog that allow you to compute some more or less approximate, for example, size of set, for example, unique numbers that people call, with some general margin of error, for example, like 2 or 3%. And for fraud detection, it's okay, right? We don't care if you did 1,000 calls in 4 hours or 1,010, right? You're a fraudster anyway. So we're trying with hyperlog currently, and it works pretty well. There are some Java Scala implementations, and they work pretty well in Flink. Okay, so that was all these problems, challenges when it comes to ingestion, execution, enrichment, and state processing by itself. Now let's move to the upper part. I guess most of you didn't see this logo, so so let's have a look what it is. And the problem that we didn't tackle so far is how to design processes, right? Because I've shown you Flink has nice DSL that lets all the developers write processes easily and deploy it and so on. But the point is that our users are not developers. They are analysts, they are revenue assurance guys, and they don't really feel like coding in Scala. They don't feel like running IntelliJ or VI or Emacs. They are rather SQL guys or Excel, right? So what do we do to help them? Well, the problem is even bigger, because we talk at the software house, right? And our clients are somewhere in different enterprise. Of course, they have different boundaries between their business people, analysts, IT team, and operations, but the biggest boundary is here, because it's the boundary between two companies, right? So it's far more difficult for them to reach to us, because we'll build them and so on and so forth. It's much easier in product companies when this barrier is just a barrier of, 1 floor in the building, right? Where the business people or analysts can just come to development team. And here, we have to try a bit harder to make them self-sufficient. So, we did, right? And this is the brief history of our project, because first we did POC with Apache Flink. Of course, it delivered great result. The performances were striking, and so on and so on. But we hard-coded all this marketing campaign. So the client reached us and said, "Okay, so how do we change the process? Do we have to come to you? We don't like this." Okay, so we'll give you this configuration file. You'll be able to edit it, for example, to change the thresholds, to change the tariffs that you want to be able to handle, and then you'll run the script. Everything will be redeployed, and everybody will be happy. It would work, but what if we would like to add some additional, I don't know, conditions for client that's not connected to thresholds? Okay, so maybe we'll do something like this. In this configuration file, you won't just write properties. You'll read simple expression in a language called Scala. It's quite easy. You'll learn it. Don't worry. And then you'll run the script, and everything deploys. You'll be happy, okay? And we tried it, and it really kind of worked. But then our client said to us, "Okay, but you had this competition during this POC. There are some guys from IBM, from SAS. They have all these nice graphical interfaces that can represent some decision trees with GUI." So we said, okay, we'll build you this GUI. You'll be able to design processes with diagrams. And what's more, we'll do it half price, and you'll let us open source it. So the client was happy, and we just had to do it. And this is how our project, Nusnacker, was born. It's open source now. If you wonder what is Nusnacker and why does it look like, the story is that Flink has squirrel in the logo, right? And Flink is based in Berlin, not in Silicon Valley like Spark. So Nusnacker is when you have bigger problem than squirrel can handle, right? And if you Google up Nusnacker and click images, this is mostly what comes up. If you like it, I have some stickers. But nevertheless, what we tried to achieve with this strange-looking guy, we wanted to achieve some certain feedback cycle for our analysts, because they usually work on some kind of warehouses, write SQL queries, maybe some Excels and stuff like that, and we wanted to make them easy to write certain processes that they can afterwards deploy, test, and check the results. Again, the results would be gathered into the data stores, and the feedback loop would close. So all the parts are pretty well understood: how to deploy stuff, how to monitor, and so on and so forth. The only lacking part is how to come from some kind of business idea, for example, written in some kind of SQL, to Flink process. And the main assumptions that we have, because of course we had pretty limited budget, was that model of the data, integration stuff, for example, sending SMS and so on, the definition of billing data will be still written by us in Scala code. And yeah, this is something that real developers must handle. And the analyst will only kind of draw diagram with certain expressions that should be kind of more or less accessible by semi-technical people knowing, for example, SQL. Right? Of course, Scala doesn't really fit in its entirety to this definition, and compiles really, really slow. But one of the biggest challenges that we want to resolve is how to facilitate testing for these business guys, because even if they design the process, it's not so obvious that they will have kind of courage to deploy it to production. So they must be able to test it and to make themselves assured that the process works okay. Right? So in fact, the idea is pretty simple. We have one jar with all our code, with the model. For example, definition in Scala case classes, the definitions of the events can be in Avro and JSON and so on. We have some configuration files where the Kafka broker is, where the SMS gateway is, and the clients prepare just JSONs through UI. and they together are deployed into the Flink cluster, and the processes run happily ever after. So how do clients work on this JSON? Well, it looks more or less like that. I like this picture because it's the prettiest user interface that I've been working on. It's still not so great, but you see the idea, right? This is just block programming. You can have some drag and drop features and so on. And when it comes to drag and drop, we have some toolbox with some generic, I would say, blocks, like filtering, splitting switches, defining the variables, and some custom-made services, which are prepared for each deployment, right? For example, one mobile operator wants to have SMSs, another mobile operator wants only have push notifications, right? So these services are written in the code for each deployment. And it's pretty easy, right? You just write some Scala code. This is the part that we do. You put it into the jar, configure it, and yeah. And then client only has to configure with expression where that's the, for example, client ID will come from, right? And then he will have defined variable describing client. So what about these expressions? We decided after kind of not so long thinking to try Spring expression language. I guess more or less of you, especially those of you who know Spring expression language, which is usually used only or mostly for configuration, right? So we managed to embed it into Flink. We even have some certain, up to a certain degree, of course, code completion, checking types, and so on. So Spring expression language is pretty, I don't know, for me it was pretty amazing to see how nice and performant it is when it comes to embedding in Flink. Of course, there are some problems. This is one of the expressions in Spring expression language that you can write. Is it readable? At least it's not Scala, right? Okay, but this is probably not what we want, and it's not really that performant enough. But the thing that really amazed me was how performant Spring expression language can be. Because this is our throughput. At peaks, it's like 150 to 200,000 events per sec, and each event goes through at least one Spring expression language expression. We have like 2 servers with kind of 40 cores or something like that. So the Spring expression language, the stuff that was written for configuration, is pretty fast. That kind of amazed me. But, of course, defining expressions is not everything. And you may very well ask, why don't you use SQL? Most of the stream processing engines currently enable users to write some SQL queries. But we stick to these filters defined one by one to get better observability. For example, our clients wanted to know which event was filtered out by the condition on tariff, which on duration, which on charge, and so on and so forth. And when you write SQL, it's not so easy to detect which condition worked, right? So, of course, filtering, enrichment are rather simple. This is rather simple stuff. But what happens when it comes to aggregations, handling state, and so on? So we figured out that we don't want to give users the full power of Flink, because it would be too hard for them. If something is too complete, it will be exponentially more difficult. So again, we have only some predefined set of aggregations written by us, tested by us, and the client only configures, for example, length of window or keys or something like that. Okay, so for them it's kind of pretty easy, and we can control more things. Now, the process is designed. What happens next, right? Because this is just a diagram. What can we do with it to make sure that our client will be able to deploy it into production? In fact, it's already happening. Our clients can prepare some kind of monstrous processes. We have like more than 50 of them running in production. As I said, we have quite large throughput, like more than 100,000 events per second. So we managed to convince them to deploy processing on production. Of course, you really want to test it. This is again from other clients of us. This is their approach to testing, which is something that we don't necessarily want to copy in our process, right? We would rather make it easier for them to test than to try out this cowboy approach. So how do we do it? This is how normally process runs, right? We have some events in Kafka, we process within Flink, enrich with some Redis events, we put the output to Kafka or to database or whatever, and the first step is kind of, I would say, sandbox testing. Maybe not unit testing, but integration tests of the process. So we run the process in kind of sandbox inside of our UI. We mock the source events. They are taken from file or from elsewhere. We don't send real SMSs. We don't send real events to Kafka. We just collect them to show the user. But the important thing is that because it's kind of user acceptance environment, we still use more like real production data when it comes to enrichment. So the client can generate some test files based on real data from real Kafka. This is when power of Kafka comes into play, because we can because Kafka is a replicated data log, and you can look, for example, last 10 or 100 events from certain topic. And then they are put to file. Client can play around with them. For example, this business analyst. And after running some tests, he can see, okay, so my test case was like 5 events, 3 were filtered out on the zero usage filter, and drill in to see what were the variable definitions, what were the event fields, and so on. Right? So these are kind of functional tests. But then we want to be able to test it on the whole stream of data, which is quite large. But fortunately, apart from real production environment, we have users acceptance test environment, which is kind of smaller copy, right? On the production, we can have like 50 jobs or something like that. And on the test environment, we have like 5 or 10. These are the jobs that currently are being worked on. And then we replicate some of the data from production. Again, it's quite easy to Kafka, from production cluster to user acceptance test cluster. So for a few days, the business guys or the analysts can analyze them, see what are the results. Of course, no real SMSs are sent. The data is just stored in some warehouses with some test flags, so they can be analyzed later. So this gives them kind of confidence when it comes to deployment on production. Okay, and all those informations are stored both in warehouse, where they appear, of course, after kind of large amount of time, and in Elasticsearch, when the analyst can see them pretty quickly. Okay, of course, this poses some challenges when we let business users define such processes with UI, because, for example, they can define too large windows. They don't know that sometimes the process cannot fit all the data into the memory, so they can be stored to disk and so on, but it works pretty nicely. And even more important for them is to have automatic monitoring, right? When they design this process, when deploy it, then we prepared kind of predefined dashboard in Grafana where they can look for kind of key metrics for them, right? They don't have to prepare it in Grafana by themselves, but they have kind of base metrics like, is the process consuming events? Are there any errors? How many events pass through the whole process? And most importantly, what is the delay? Right? And of course, we have additional metrics that generate some alerts or test messages for us when, for example, something bad happens and delays on consuming events from Kafka are pretty large. This is one of our latest failures, I do believe. Or sometimes we want to detect something else. Our part is processing fine, but the events don't come into our production system, and because some source systems had their own failures, and we have to detect them. Okay, so the main points that I've learned during this project, the first one is just use Kafka and be happy with it. When we gave it enough resources and didn't put too much other systems on Kafka servers, it works really reliably, really performantly, and I highly encourage you to use it. The next thing is try to think about this data flow, about this kind of feedback cycle that you want to achieve with your analysts and SQL guys. We've seen that it's possible not only for kind of batch processing or simpler systems, but also in stream processing at large scale. And when we did it, the thing that helped us really nicely was we started with some simple stuff, with filtering, stateless processing. Only then we passed to enrichment, for example, with getting client data and so on. And only then, when we are kind of pretty sure that we can handle that case, we move to different, more complex use cases like aggregates and so on, which themselves, of course, present you with, well, many additional challenges, right? And also, it's good to start safe. At first, we just put the data into some warehouse, to some monitoring solutions. Only then, when we are really sure everything is happy, I mean, the business has confidence with us, we send SMSs, and now we can handle most intrusive actions like blocking account, which can be really kind of painful both for the client and mobile operator when not the fraudulent client is blocked but the good one. Okay, and another thing that helps us with testing and with deployment is that when it comes to stream processing, it's quite easy to replicate the traffic, to replicate the behavior of the system to user acceptance test environment, right? Because the flow is like one way. And it's easy to monitor and detect some problems, both performance and acceptance. And monitoring, of course, is the key. If you want to try Nusnacker, then go to GitHub. It's there. Well, there's still a lot of work ahead of us, but I think it's kind of nice tool that maybe can help somebody. And if you want any questions and so on, I'll be around for like an hour or so. Thank you very much.